Okay, in this video I want to talk a little bit more about this concept of the phasor and where it comes from. So remember, we have some function v of t is a magnitude times the cosine of omega t plus phi. And so remember that Euler's relation tells us that e to the j theta is equal to cosine of theta plus j sine of theta. And this is polar and this is rectangular. We can have some shorthand notation that says the real part of e to the j theta is cosine of theta, and the imaginary part of e to the j theta is sine of theta. So our Vm cosine of omega t plus phi, this is the entire argument. This is the theta, this omega t plus phi, could be written as Vm times the real part of e to the j omega t plus phi, which is Vm times the real part of e to the j omega t, e to the j phi. Now, if you know differential equations, and even if you don't, okay, I can just tell you that if you have an equation and you have e to the j omega t, it doesn't matter what you do to that. You can take its derivative, you can take its integral. You're going to generate back something times e to the j omega t. In other words, the exponential function, whether you differentiate it or integrate it, and no matter how many times, you always get the. So one thing that we know about surfaces common to all currents and voltages. So I can ignore it. Ignore e to the j omega t. We're going to remove it from our expression because we can put it back because it's going to be common to everything. So it's kind of like it's there, it's in the background for the ease of calculation. We're going to ignore it. We're also going to ignore our real notation. Once again, knowing that it's there, it's in the background, it's running through every calculation we do. We'll fix it at the end of the solution. So we're going to ignore that as well. So what that means is our Vm cosine of omega t plus phi, when it undergoes the Phasor transformation, and you notice here I have not used equal, I have used a double arrow. That's what I use to indicate transform. It'll give me the magnitude times e to the j phi, where phi was the phase in my original function and b was the magnitude. Now let's talk a little bit about inductors and capacitors. For an inductor, v of t is L di dt. If I assume that I is an AC function, so it's I magnitude cosine of omega t plus phi, and I let this cosine of omega t be written as the real part of e to the j omega t plus phi, which is e to the j omega t and times e to the phi with j phi. This is not time dependent, so It's not gonna cause a problem when I take its derivative. It's just gonna look like a constant. So I can write that for the moment, ignoring the real notation. Let's call that Im e to the j phi e to the j omega t. So now I want to take this and substitute it in for current, which tells me v of t is L di dt. Substituting that in for I, this first part is a constant. So it's Im e to the j phi, and then the derivative of this, which is j omega e to the j omega t. Okay, and once again, this real notation is implied. It's not affecting one way or another how I take the derivative. So I just kind of took the derivative inside the terminology. It's there for now. We're just going to live with it. So once again, I'm still in the time domain here. So let's simplify this. This is j, and I need an L. So this is j omega L Im e to the j phi e to the j omega t. And so now what we're going to do is consistent with our, and that's v of t. So now consistent with our understanding of the Phasor transform, we're just going to do a Phasor transformation on this entire equation. So v of t just goes to v the Phasor. That's j omega L Im, and this e to the j phi becomes angle phi, and the e to the j omega t, because I'm expressing it in the Phasor domain, and this is basically the omega t part of the cosine function, that's going to go away. Remember, when we go to phasors, we drop out the real notation, we drop out the e to the j omega t part. Okay, so v the Phasor is j omega L, and then notice right here, this is basically what our current was. So if we were to have taken our current and written it as a Phasor, it would be Im angle phi, which is what we've got right here. So, so that is what we have when we do a Phasor transform. So what this means is v looks like some I times what we will call z. This is the impedance, and we talked about that in the previous example where we looked at impedances of inductors, capacitors, and resistors. So once we express an inductor as an inductive impedance, then we can express a voltage as a current times that impedance. This is only in the Phasor domain. So once we've done that, then we have to transform back to the time domain. All right, so this is stuff that was actually covered in previous PowerPoint lectures. I just wanted to give you a second look at it with a slightly different way of presenting it than what's shown in the textbook slides, so that if that's confusing to you, which it kind of often